Let us now come on to the second part of the theory of relativity. We have seen that two pillars of classical relativity, namely the length and time, which were taken to be absolute, found to be no more absolute in relativistic domain. Length appears to be contracted and time appears to be dilated. Now we are going to examine the third pillar, namely the mass. Classical relativity predicts that mass is absolute, and in all the Newton's laws of motion, etc., we have taken mass as to be constant. Let us see relativistically, does mass remain constant? Since mass is not involved in Lorentzian transformations, so we can no more use these transformations directly. So we have to go to first postulate of the theory of relativity. That is, the physical laws remain invariant in all inertial frames of references. Since physical laws remain invariant, we have to revoke a physical law which involves mass. The simplest law which I can think is the conservation of momentum in collision. The momentum is a product of mass and velocity, and therefore the observance of conservation of momentum will give me or will predict whether mass remains absolute for the two inertial observers, one is at rest and another in motion or not. We consider an experiment in which two identical particles collide. We consider one particle A in S frame and another particle B in S dash frame. S dash is moving with respect to S in the direction of axis of X. We consider the particles to collide in Y direction, because if we consider their collision in X direction, length contraction will come into the picture. We want to avoid it to simplify mathematics, and therefore we consider the two particles to collide along Y axis. Since S is moving with very high velocity V and a particle A is moving with a velocity VA which is quite less, much less than the speed of the frame. Therefore, when A moves in minus Y direction and B moves in Y direction, and they will collide at Y by 2. After collision, they will bounce, they will retrace their path. If we observe that in S frame, A is at rest and S dash is moving, then obviously the collision will occur at a distance Y. We consider the behavior of A in S to be identical with the behavior of B in S dash. That is, MA is equal to MB dash, and this is their rest mass, M0. The velocity of particle A is Y upon TA, time taken by A in colliding, and VB will be equal to YB upon TB dash. I call it VB dash. Now see, if we observe the collision from S, then S is at rest, so this moves very slow and the collision occurs as seen by S. The collision seen by S dash will be other way round. That means B will be colliding and bouncing back. Here A is colliding and bouncing back. That will be the collision. So from momentum conservation observed in S, MAVA must be equal to MBVB. I can write MA for VA, this is capital VA, or we can say V small VA, doesn't matter, it will be small VA here, it will be small VB here, doesn't matter. MA, Y upon TA this will be equal to mb y upon tb. See that Ta is not equal to Tb. Ta is equal to Tb dash. Ta is equal to Tb dash, and it is the proper time because A is at rest in S and B is at rest in S dash. Therefore, I can further write this is relativistic time mb y upon Tb dash under root 1 minus v square by c square. mb y upon b dash, this is y, Tb dash, this will be equal to Vb dash under root 1 minus v square by c square. Ma, Va. Va is equal to Vb dash. These are equal, so they cancel out. And therefore, what do I have? Mb is equal to Ma under root 1 minus v square by c square. Ma is proper mass, so m0 under root 1 minus v square by c square. This is greater than m0. So what do we find is that mass appears to have increased on motion. That means as a material particle moves with a very high speed, its mass appears to be increasing and goes on increasing. Mass goes on increasing. If we want, we can draw a graph m upon m0. This almost remains v by c. This almost remains constant and suddenly increases to infinite at v equal to c. This is 0.8. This is 0.6 and so on so forth. So mass increases quite fast as velocity approaches v equal to c. Question is, where from this mass is coming up? Gentlemen, don't be confused with the definition of mass, that mass is the content of matter. That means number of molecules. No, that is not a correct concept relativistically. Mass is the inertia to motion. So as velocity increases, the mass increases, means inertia offered by each molecule increases. It is not that number of molecules are increasing. That is the concept, relativistic concept of increase in mass or relativity of mass. So see that the third pillar of Newton has also fallen down. That means the classical relativity is not acceptable at very high speed. That means when velocity of the particle or velocity of a material particle is approaching c. One very important thing here, see that m0 is equal to m under root 1 minus v square by c square. If v equal to c, m0 is 0. That means if a particle moves with the speed of light, it must have rest mass 0. The two examples which I can cite is, one is a photon that has a rest mass 0, another particle which is emitted in beta decay, that is neutrino. Neutrino also travels with c and therefore it has rest mass 0. Let us now consider where from this mass increase comes up. The answer is very simple. As mass approaches, as the speed approaches c, you see no material particle can achieve speed of light. And therefore, as we increase its speed, that means as we give energy to this particle, a part of energy starts going to the mass, and as a consequence, mass increases. So there is an obvious answer to this question, that if the mass increases, where from this mass comes up? The answer is very simple. This mass comes up from the energy. That means mass and energy should be simply related. Before we go to the mass energy relation, let us see how the velocity addition, the classical law of velocity addition behave. To find out the velocity addition, let us come to Lorentz transformations again. X dash x minus vt upon under root 1 minus v square by c square. Y dash is equal to y, z dash is equal to z, and t dash is equal to t minus vx upon c square upon under root 1 minus v square by c square. How to find the velocity of a particle in a particular frame? So velocity is rate of change of displacement. Obviously, Vx will be equal to dx by dt. And Vx dash will be dx dash by dt dash. Gentlemen, please be careful. Dx by dt dash or dx dash by dt, they are meaningless. They are meaningless. And therefore, to establish how does velocity add relativistically, we differentiate this Lorentz transformations with respect to an absolute variable, the variable which does not change with time, and we see dx dash will be equal to dx minus v dt upon under root 1 minus v square by c square, and correspondingly dt dash will be equal to dt minus v dx by c square upon under root 1 minus v square by c square. We divide these equations. Divide first equation by second equation. This will give me dx dash by dt dash, that means vx dash will be equal to dx minus v dt divided by dt minus v dx by c square. Dividing this by dt in the numerator and denominator will give me vx minus v upon 1 minus v vx by c square. This is not equal to vx minus v. See, the classical law of velocity addition, that means Galilean addition of velocity, is untrue relativistically. Second important aspect is here. Similarly, dy dash by dt dash will be found to be dy dash by dt dash is equal to dy divided by dt minus v dx upon c square. This will give me vy upon 1 minus vvx upon c square, and similarly this is vy dash. Similarly, vz dash will be equal to vz 1 minus vvx upon c square. Classically, the motion in y-axis is not affected by motion in x direction. However, relativistically, see, vy dash is not equal to vy, but it involves vx. Where from does this come? The answer is, see Lorentz transformations, x involves t and t involves x. And that is the concept of Albert Einstein, that space is not three-dimensional, x1, x2, x3, but it is four-dimensional space, and fifth dimension is imaginary dimension, and that is the time dimension. So here is Einstein's four-dimensional space. That means relativistically any event has to be described in terms of not only space coordinates, three space coordinates, but also an imaginary time coordinate, fourth coordinate, iota ct. I is square root of minus 1, that is imaginary, or jct, whatever you like. Therefore, because the space is four-dimensional, the velocity in x direction is affected by velocity in y direction. If we take reverse Lorentz transformations, we can write Vx will be equal to Vx dash plus V upon 1 plus Vx upon c square, etc. So we can have velocity addition. If two particles traveling in opposite direction, this relation will work. If two particles are traveling in the same direction, then this will work. If the velocity of the frame, this is the velocity of the frame and this is the velocity of the particle, then the velocity addition will be like this, and if they are moving in the same direction like this, then the relation will be like this. That is the relative velocity formula. So relativistic velocity addition is different from classical velocity addition because the space is a four-dimensional space. To a very, very important relation known to even a layman, mass-energy relation. That mass is no more different from energy. Interesting thing is, why mass is related to energy? We have seen while discussing the variation in mass that when a particle travels with very high speed, its mass increases. Where from this mass comes up? The answer is very simple. Since no material particle velocity can exceed the speed of light, and therefore as we accelerate a particle, give energy to the particle, a part of energy goes to the velocity or a speed and a part starts going to its mass. That means mass and energy should be simply related. And that second part, that also follows that as the speed becomes higher and higher, more and more energy goes to the mass and less to the speed, because c is ultimate achievable velocity. So let us find out. So we consider a particle, and this particle is applied with a force. Obviously the application of force will increase its momentum and hence its energy. So F is just force is equal to rate of change of momentum. Then work done on the particle, TW, will simply be equal to F dot dx or F dot dr, whatever you call. F is equal to dp by dt dot dx, or dr you can say. If you want, you can take F dot dr, doesn't matter, absolutely does not matter. I can write dmv dx by dt, and this is simply dm v plus m dv. Mass is no more constant, dot v. This gives me dm into v square plus mv dv. This is the work done. Since variation in mass is coming up here, dm, we use this relation m is equal to m0 upon under root 1 minus v square by c square. To simplify mathematics, what we do, we square it and write down 1 minus v square by c square, m square is equal to m0 square. Multiplying entire relation by c square minus v square, m square, this is equal to m0 square c square. Differentiating we have. Differentiating we have c square twice m dm minus twice v dv m square minus v square twice m dm is equal to 0. We have to find the value of dmv square plus mv dv. Do we find this? Yes, we definitely find it. 2 we cancel throughout, or 2m we can cancel throughout. C square dm is equal to mv dv plus v square dm. This is the same relation, dmv square plus mv dv, mv dv plus v square dm, and therefore dw comes out to be dm into c square. So work done when its speed, mass increases from m0 to m, dm into c square. This is equal to mc square minus m0 c square, and this is the kinetic energy. So kinetic energy of a particle moving with very high speed is not half mv square, but it is mc square minus m0 c square. That is the kinetic energy of the particle. Now in kinetic energy of the particle, there are two terms. One is mc square and another is m0 c square. m0 c square can be taken as rest energy. So what is the total energy of the particle? Total energy is equal to kinetic energy plus rest energy. And this comes out to be mc square. Therefore, energy of a particle of mass m is mc square. It is not half mv square and so on and so forth. So total energy of a relativistic particle is mc square. Whatever be its velocity does not matter. The total energy will be mc square. The kinetic energy is obviously mc square minus m0 c square, and it is not half mv square. We generally mistaken if we write that kinetic energy of a particle is half m0 v square upon under root 1 minus v square by c square. This is incorrect. Why incorrect? Because we have not considered the relativistic concept of the velocity addition, and therefore this is not a correct expression. Let us see how do we write relativistic energy and momentum. This is needed to discuss relativistic kinematics. We are not going to discuss it, but I am just opening a way how to discuss the relativistic mechanics. So to discuss relativistic mechanics, the essential thing is we must have relativistic energy and relativistic momentum. Relativistic energy, as we have seen, E is just equal to mc square, which can be written as m0 upon under root 1 minus v square by c square into c square. This is the relativistic energy. What is the relativistic momentum? Relativistic momentum will be equal to mv, and obviously this will be m0 upon under root 1 minus v square by c square into v. How do energy and momentum are related? To relate energy and momentum, we square this. P square and multiplied by c square. We should have this is p square c square. And to this p square c square, let us add m0 square c4. Once we solve it, we will find that we come out to, this comes out to be this is E square, and therefore relativistic energy E is just equal to square root of P square C square plus M0 square C4. This is a very, very important relation because energy has to be written as mc square and this energy is equal to P square C square plus M0 square C4. For a photon which we have seen has a rest mass 0, the energy is just Pc, or this is equal to h nu by C. Why h nu by C? We multiply it by C and divide by C, energy is h nu. E is equal to h nu. We can see it like this. We can write h nu, this is equal to P into C. This gives momentum to be h nu by C. We commonly use this relation while discussing the impact of light with material particles. So we have seen that how to discuss relativistic energy, momentum and relativistic kinetics. Now it's time to ask few important questions. First question may be, suppose a rectangular sheet, for simplicity I take as a square sheet of dimension A, is moving with velocity v comparable to c. How do area of this sheet will look like? The answer is very simple. Only the length in the direction of motion gets contracted. The length transverse remains invariant. Why? Because of Lorentz transformations, y dash is equal to y and z dash is equal to z. Only x contracts. Therefore, only this side will contract. This will look like a rectangle and therefore area will be equal to A0 square root 1 minus V square by C square. Similarly, what shall happen to the volume? Obviously, in case of volume also, only one dimension will contract and we can write V is equal to V0 under root 1 minus V square by C square. Volume will contract by a simple relation. Not all the three dimensions will contract. Only that dimension contracts which is in the direction of motion. Second important example I can take is whether one event is simultaneous in a one frame, will it remain simultaneous in a moving frame? Let us see. This is a very big thing. Is simultaneity absolute? Let us see whether the two events which are simultaneous in S, shall they appear simultaneous in S dash? They are located at two different places, both in S and S dash. So to see whether they are simultaneous in S dash or not, we find out T2 dash minus T1 dash is equal to, we substitute from Lorentz transformations, T2 minus Vx2 by C square upon a square root of 1 minus V square by C square minus T1 minus Vx1 upon C square root of 1 minus V square by C square. Therefore, T2 minus T1 under root 1 minus V square by C square minus x2 minus x1 V by C square upon under root 1 minus V square by C square. See that two events 1 and 2 are occurring at two different places simultaneously. That means x2 is not equal to x1. Since x2 is not equal to x1 and therefore T2 dash minus T1 dash is not equal to T2 minus T1 either, or even not equal to T2 minus T1 upon square root of under root 1 minus V square upon C square. That means dilate not equal to time dilated, and therefore two events which are occurring simultaneously in one frame will never be simultaneous in another frame if they are occurring at two different places. This is wonderful result of theory of relativity. That means you cannot directly connect two events at different places with time at the same time. This is also repercussion of Einstein's four-dimensional space. Now, let me give me few examples of mass-energy relation. See, mass converting to energy is one aspect and energy converting to mass is another aspect. There are numerous examples where mass is converted to energy. The best example ever given is of nuclear fission and nuclear fusion. In nuclear fission, uranium-235 is bombarded with slow neutrons. The bigger nucleus breaks up into two equal-sized, almost equal-sized nuclei, and there is a release of enormous energy. When we put an energy balance, mass energy balance, we find that the release in energy is a result of the defect in mass or loss in mass. That is one example. Similarly, another example of nuclear fusion. And this nuclear fusion is occurring in all the stars. Basically, the source of energy in stars is nuclear fusion. Under the strong gravitational force, the heavy nuclei field, the lighter nuclei, say hydrogen, they collide at a high speed and coalesce into a helium atom. Then helium atom, when helium atom is formed, its combined mass is less than the combined mass of the deuterium atoms. The loss in mass is the source of energy. These helium then further collide and form carbon or nitrogen atoms. And cycle is repeated. These atoms break up and break down. As a result, there is a continuous source of energy in the stars. When this equilibrium is broken up, that means most of the energy is exhausted, ultimately stars dies, and thus age of the stars are calculated theoretically. What will be the age of the star? The another part, energy converting into mass, comes up from pair production. What happens then when a photon of energy greater than 1.1 MeV passes near a heavy ion, it breaks up into electrons and positrons, and thus a shower of electron and positron is formed. This is the research of Homi Jahangir Bhabha, where he established that these electron-proton showers coming in cosmic rays is a consequence of this pair production. And here what we see, that we are producing mass from energy. This is another example where energy is converted to mass. So answer is very simple. Mass can be converted to energy and energy converted to mass. To the lighter side, I can say that this was the concept of ancient saints of India, that they used to stand before sun, absorb sun rays, and it is said that they converted it to the useful energy and they can live without eating and drinking. Thank you very much.